with differentiation, we have this nice operator, and this is like, take the derivative, right? We don't really have that yet for integration. So we want to define something very similar. And so we're going to define, how do I want to say this? Yeah. So if f is a function, we define this thing. Okay, no bounds of integration, right? No bounds of integration. To be the set of all antiderivatives of f. Okay, so for example, we have the integral of like x squared dx. So that's going to be x cubed over 3. And then, you could write this in set notation, but often we're just lazy. And we say it's x cubed over 3 plus c, where it's understood that c there is allowed to range over all real numbers, right? Because, again, every single antiderivative of x squared is going to look of this form, right? And yeah, if I let c range over all real numbers, I get them all. Okay, so that's why we often write that. Now, in particular, though, what this means is that if you do not include the plus c, your answer is incorrect. Because this thing is a set of functions, but if you don't include the plus c, then you're just saying it's equal to a function, right? You get a type mismatch. So instead of being a function, or instead of being a set, you just get a function. Now, notationally, what this means, though, is that we've overridden the integral sign a lot, right? We've used it to mean a lot of things. So let's say, let's note the following. So the integral from a, b, f, integral of f, integral a, b, f of x, dx, these are real numbers, right? Okay, the integral from a to x f, and the integral from a to x f of t dt, these are functions. Right? Like my antiderivatives, these are my accumulator functions, that sort of thing. And then the integral from f of x dx, this thing is a set of functions. So we've really overridden, right, what the integral sign can mean. And context will usually tell us what the appropriate thing is, but we do have to be a little bit careful here. Right? So pay attention to what you're sort of being asked to do. Pay attention to how you use this notation. Make sure that you try and use the notation correctly. Because depending on what you write down, it could be a number, it could be a function, it could be a set of functions. Right? So just be careful about that. So in this case now, we sort of have that notation which allows us to say take the antiderivative. Right? We have a notation that says take the derivative. Now we have a notation that says take the antiderivative. Okay? Okay, that's all I want to talk about in terms of indefinite integrals. So now we're talking about logarithms. No, I just did that. All right, now obviously this is the opposite of what you would have learned in high school. So in high school, you usually learn about what an exponential is first, and then you define the logarithm to be the inverse of that map. And of course, the reason why that is nonsense is because you have no idea what like 2 to the power of x means, right? As a function, that's nonsense. You can't, because like, how do you raise 2 to the power of a real number, right? Like, what is 2 to the power of pi? Sure, we can do 2 squared, no problem, right? That means 2 times 2. We can even do it to a rational number, right? 2 to the power of 3 halves means the square root of 2 cubed. All of that makes perfect sense. But if I choose an irrational number, and I do 2 to the power of pi, that's nonsense, right? So in high school, they just sort of like wave their hands, they did a little magic to like pretend that this makes sense. But in practice, right, that was nonsense. They couldn't do that. You can, but you need, like, you have to define what 2 to the power of pi would mean or something, right? Okay, so if we want to do that like in the strictest of logic, then we either need to, I either need to define for you the function like 2 to the power of x, and that's quite tricky. It requires some work. We'll be able to do that in a couple of weeks, but we're not really at a stage where we can do it now. The way we're going to do it, and to be completely rigorous, is to actually define the logarithm first and then define exponentials to be the inverse of the logarithm, right? Which feels backwards, because it is. Okay, so here's how we're going to do it. So let's say note, or we know I'm going to help motivate this. So we know that the integral of x to the n dx is x to the n plus 1 all over n plus 1 plus c for any n not equal to negative 1, right? Right? That's just by the power rule. If we do the power rule in reverse, this is what we would get. But when n is equal to negative 1, we're in trouble, right? I.e., we don't know. We don't know the integral of 1 over x. Right? Okay. And in fact, no matter how hard we think and how hard we try, none of the functions we have so far, polynomials, radicals, quotients, products of those, sines, cosines, no matter what we do, we can't come up with an antiderivative for that thing. So what do? We define a new function which is its antiderivative, right? So definition, the logarithm is the function that maps 0 infinity to r, and its output, let's do 1 over x, 1 over t, like that. Okay? So we don't have an antiderivative for 1 over x, so we're going to define a new function, and that's now its antiderivative, right? We're going to define log to be the antiderivative of 1 over t. Okay? Notationally, a couple of notes to say. I said the logarithm, and some of you are probably thinking, well, okay, wait a second. We learned in high school there are different bases for the logarithm. Nonsense. Those are not things. This is the logarithm. It is the only logarithm, okay? There are many things that sort of look like it, but those are pretenders. This is the logarithm. Okay? The second thing is like, oh, well, in high school we called that ln, ln. No, okay? That's what physicists do. Dirty, dirty physicists. We are mathematicians. This is log, okay? And this will always be log. And in this class, if I write log, that is what I mean, okay? And yes, some people call that the natural logarithm. Again, it's only the logarithm, all right? So mathematically, this is log. None of this, what is its base nonsense stuff. Okay. Now, there are a couple of things about this we can prove immediately, right? Things that you would have learned about this function. And again, I want you to be careful about using the facts that you think you know about this, right? We have to be rigorous. We have to make sure that we prove them. But there are a lot of these facts that in high school you were just told were true, but you couldn't possibly prove them. Now the proofs are very straightforward, right? So proposition. So 1. Okay, log of 1 is equal to 0. All right, you probably could have done that even in high school, right? Just by definition of the logarithm, that would have been true. 2. Right, 3, what do I want? I want L as the log is function strictly increasing, and right, okay. So, log is strictly increasing, and 4, log x is less than 0 if x is less than 1, and log x is greater than 0. Greater than 1. Okay, I'm not going to prove this because it's true, right? It's absolutely true. Log 1 is equal to 0. Why? Well, because the integral from 1 to 1 is 0, right? Doesn't matter what you put there. If you integrate on a single point, there's nothing, there's no area, right? So log 1 is 0, trivial. 2, the derivative of log x is 1 over x. That's the fundamental theorem of calculus, right? Log x is defined to be the antiderivative of 1 over x. Well, then what does that mean? The derivative of log x is 1 over x. Great. Log is strictly increasing, trivial. It follows from 2, our function is 1 over x, but the domain of our function, right, where did I put the definition? The domain of our function is 0 infinity. So this is always greater than 0. And remember, right, by the mean value theorem, if your derivative is always greater than 0, you're a strictly increasing function. Right? Everyone agree? And then 4 follows from 3 and 1. So your strictly increasing function, at 1, you're equal to 0. So to the left of 1, you must be less than 0. And to the right of 1, you must be bigger than 0, right? Because you're strictly increasing. Does that make sense? Right? Like, you draw a function. At 1, You go through 0, you're strictly increasing. How are you possibly going to draw anything other than, you know, being less than 0 to the left of 1 and being greater than 0 to the right of 1? You can't, right? So there's nothing to do there. The proof is true. Okay, so those are some facts. And I think you wouldn't have been able to do that in high school. You probably could do it if you learned calc in high school because this fact is still true. This fact is sort of like tricky to prove in high school, but like whatever, here it's trivial. All right, now let's prove some other facts. Now these are facts that I think you could have proved in high school, but I think their proofs are a little bit messier. So let's see. So here's the proposition. Now where do I want these to be? Just real numbers? Yes, 0 infinity, 0 infinity, right, okay. So what? So for all x and y, 0 infinity, right? Somebody you should all double check my log identity zone to make sure I don't screw them up. The log of 1 over x is negative log x, and 3 over x, and 0 infinity, and rational. So right now we're only going to be rational. That's true, right? Those identities should look familiar. To prove this, again, in high school, you have to use the fact that it's the inverse of the exponential, and you've got to do some manipulation. And those manipulations, while not terrible, are a little bit of work. Here, these proofs are actually pretty quick. The proof of 1 is a little bit tricky, but it's not too bad. Okay. So the proof of 1, this is a really slick proof. So what we're basically going to do is we're going to fix a y right off the bat. Okay? So proof 1. Let's fix y in 0 infinity, and let's say let f sub y of x be log xy. Okay? So I fixed y. Basically, we don't know how to deal with functions of 2 variables right now, right? And x and y both look like variables. So why don't we just fix y and let x be a variable? Okay? That's what I'm saying. So y is just a number. Okay, so now the derivative of this function. So we're going to use our chain rule. So we're going to get 1 over xy times y. That's 1 over x. Okay? So immediately this actually tells us something pretty cool. Log, if you have the logarithm function and you just have like log 7x, the derivative of log 7x is still is still 1 over x. Right? That scalar there doesn't make any difference to the derivative. Right? And again, it shouldn't, because log 7 times x is going to be log x plus log 7. The log 7 disappears when you differentiate, right? It's just a constant. Okay, but what are we proving here? So this thing has the same derivative as log x, right? And this thing's derivative is the same as log x, therefore it's equal to log x plus some constant, right? So since f prime y of x is equal to log prime of x, there exists some k in R such that fyx is log x plus k, right? If we want to figure out what k is, all we got to do is specify an initial value. So let's try 1. 1 seems like a pretty good number. Right? So if I plug 1 into both sides, this just becomes log y, right? Because the function is log xy. So if I plug x equals 1, that just gives me log y. If I plug it into the right-hand side, log 1 is 0, and so I just get k out, right? So k is log y. So what have I just proven? Log xy is log x plus log y. Right? Because my function is log xy, So that means log xy is log x plus k, but that k is log y. So I'm done. Everyone good? All right. Okay. Assume yes, unless somebody yells at me. All right, 2. Now this is a fun one. In fact, I think I made you do something very similar to 2 and 3 earlier in the year, right? So for 2, let's see. Well, not even really 2, I guess. But let's, what do I want to do? Yeah. So fix x is 0 to infinity. And we get log 1 is log x times 1 over x, which is log x plus log 1 over x, right? That's 0. So solve this for log 1 over x, what do you get? You get negative log x. Right, okay, 3. 3 is a little bit more work. 3 is the thing that I made you do sort of at the beginning of the year, but that should bring some up. So 3, to prove this is true for all rational numbers. And like anything, if you start right away with rationals, it's going to be too hard, right? So don't start with rationals. Let's start by proving it for naturals, then do the integers, then do the rationals, right? So naturals first. So let n be an n. So that log x to the n so that's true, right? That's the definition of what x to the n is. You just multiply x by itself n times, because n is a natural number. Well, and I didn't prove this explicitly, but you can imagine you can just apply part 1 inductively, and this will become this. Voila. Right? Great. We proved it for the naturals. That's what we wanted to do. Okay? So now let's extend it. Let's prove for the integers. So I need to prove it for the negative numbers. But again, there's really nothing to do there, because we know what log 1 over x is. So, moreover, all right, actually, maybe we should do 0 first. Like log of x to the 0 is equal to log 1 equals 0 log x. Right, okay, so it's true for 0 as well. So now let's do it for the negative numbers. And if m is a natural number, so again, I'm just going to take it to be positive, and then I'm going to put a negative sign in front of it to deal with it. And log x to the negative m is log 1 over x to the m is equal to log 1 over x times 1 over x times 1 over x m times negative log x minus log x minus log x m times great, so it's true for negative numbers as well, right? So anytime you're doing any of these things, you're trying to prove it for the rationals, this is usually your progression, right? You prove it for the naturals, you prove it for the integers, and then you build up to the rationals. So I've proven now for every integer, this identity is true, right? If I take log of x to that power of the integer, we take that integer and pull it in, right? And put it in front of the log. Okay, all that's left is the rationals. Rationals not too bad, right? And again, it's sort of the typical trick, which is to say, well, I know that a rational basically looks like an integer over an integer, so why don't I just rewrite my fraction and basically get rid of the fraction and then use this identity, right? So let q equal a over b be a rational number, so that a is equal to b cubed. right? So I start with my rational, but I don't know how to deal with fractions. So let me get rid of the fraction and write a is equal to bq, right? And now I'm going to act on log a, right? So log a is equal to x to the a is a log x, right? Okay. But this is also equal to log x to the bq, right? Which is log, here, maybe let me use square brackets here, x to the q. I don't know how to deal with x to the q, right? I don't know how to deal with the rational power. But I do know how to deal with the integer power. Like that, right? So I take this, and I solve for log x to the cube, divide both sides by b. Right? Does that sort of remind you? I think it was like assignment 1 or something, right? I made you do something like this, right? So great, there we go. We'll prove those 3 facts of the logarithm. All right, everyone's good? So you now, luckily, have enough to do your next homework assignment. Maybe let me do one more thing, because if I do this one last thing, you'll actually know what to do for your next homework assignment. So, let's prove E exists. Euler's number. So, if I was feeling really, really mean, this would be a test question. You know, it's really, really easy. There exists a positive real number such that log E equals 1. Right? That's Euler's number, right? You guys know that. That's Euler's number. How to do this? This comes up on the test. What would you do? Let's think about, I didn't tell you to figure out what it is, right? I just told you to prove it exists. So what theorems do we have that tell us, prove that a number exists, prove that there's a solution to this equation?
The value theorems?
Sure, yeah, absolutely. Now, which value theorem do we want to use? So we don't know, we do know log is continuous, by the way. I guess I forgot to mention that, right? But log is continuous because FTC 1 tells you that antiderivatives are continuous. Okay, so we have continuity, so we can immediately use our value theorems. So the question is, do we want to use extreme or do we want to use intermediate?
Intermediate.
Intermediate, okay, so if I want to prove log E is equal to 1, using the intermediate value theorem, what do I need to prove?
There exists there exists A such that log A is less than 1.
Yeah.
And then there exists B such that log B is greater than 1.
Great, yeah, I just need to prove log takes on some value less than 1, some value bigger than 1 by the intermediate value theorem. I'm done, right? Okay, well, there's definitely a value of log that we know for sure gives us a number less than 1. What?
1.
1. Log 1 is 0, right? So we just need to find a value of log that's bigger than 1. And we've proven log exists. Okay. So we know log is continuous. To apply the intermediate value theorem, let's find A and B in 0 to infinity, such that log A is less than 1 and log B is greater than 1. Okay? But set A equal to 1, right? Because 0 is less than 1. Now, A equals 1 clearly works. So we need B. Anyone got any ideas of how I find a b? In fact, does anyone have, let's cheat a little bit, let's cheat. Anyone if you had to guess a b that'll work, right? Knowing what e is you're sort of cheating, right? Like you know what e is, 2.71a28. What value would probably work? 3 would probably work, right? But 3 might be cutting it a little bit close because e is already 2.7 something, so that may be hard to prove. I think log of 4 will probably work, right? So let's try and show that b equals 4 works. And then you might say, well, like, how the hell do you expect me to compute the integral of 1 over x from 1 to 4 if like this is its antiderivative and it's the thing that we're trying to do, right? Well, you don't actually have to compute log of 4. You just need to prove log of 4 is bigger than 1, right? I.e., you can use the Darboux sum and prove that it's bigger than 1. Let me show you what I mean. So here's what we're going to do. So what does log look like again? Log looks something, here's 1. Log looks something like that, right? Okay, so here's 1, 2, 3, 4. All right, let's use a lower sum. And again, we could use more numbers if we want. But what we'll do is we'll take a lower sum. We're doing 1 over x. What am I talking about? Right? Because that's the function we're integrating. So we want to do 1 over x. So 1 over x looks something like that. So let's use a lower sum. Right? And this function is actually monotone. Right? It's monotone decreasing. So we know that the minimum of this function is always going to be its right endpoint. Right? So I don't even need to take a tricky partition. I can just take the partition that is 1, 2, 3, 4. And hopefully that'll work. And if it doesn't work, we'll add in another point. Hopefully that'll work. Okay, so let's try 4. Let's see if that works. So we claim log of 4 is bigger than 1. Okay? To do this, let P be the partition 1, 2, 3, 4. Right? It's the only time in your life this partition is ever going to be this nice. Okay? Let P be 1, 2, 3, 4. So LF or L log on P is equal to what? So on the interval 1, 2, it's going to be 1/2 times 1 plus 1/3 times 1 plus 1/4 times 1. Right? These ones are the lengths of each of the intervals, and then the 1/2, 1/3, and 1/4 is the infimum of the function. Right? Everyone agrees? Okay? And what do we get when I add this up? So let's make everything base or a 4. So I get 12? 12 is right? So I get 6 12s plus 4 12s plus 3 12s. Look at that. Sorry, not log, 1 over x. Right? So log of x, log of 4 is the integral from 1 to 4 over x dx. Right? So we're done. So E exists. It was just that easy. Now we have no idea where it is. We know it's somewhere between 1 and 4. Right? We can't do much better than that. But right now we do know that there is a value which makes this function equal to 1. Great. Everyone's happy? Happy-ish? And then, again, if you want to know what the value of E is, you would actually use a computer and you'd start to try and figure it out, right? You'd do some computations, try and work it out. Okay. Without sort of hurting your brain too much, maybe I'll leave for you this next part. We'll leave this until next week. But so at this point, we've proven everything we want to prove about log. Okay? So the next thing is to prove that e to the x exists, the exponential function. What would you do? Right? So the first thing we do is say, well, listen, log is injective. Does everyone agree log is injective? Why is it injective? Yeah, strictly increasing, right? So it's an injective function. So it's injective, which means it's invertible, so we have the exponential function, right? Just call it exp for now. We don't know it looks like e to the x or anything. We'll just call it exp. All right, how would we find the derivative of the exponential function? What theorem did we learn that tells us how to compute the derivatives of the inverse function? Yeah, okay, it's in the name, right? So it's the inverse function theorem. So we use the inverse function theorem, we can prove that the derivative of the exponential function is the exponential function, right? Do that as an exercise. And then the only thing left to do is to prove your exponential identities, right? Prove that. All right, what should that be?
X A plus B.
Right. Okay, x a to the power of b should be what?
X A times B.
Yeah. And then x to the negative a should be
1 over X A.
right? And those are all the properties of the exponential function. Right? And you'll prove each of these from the logarithm, right? The logarithm has a corresponding, right? Log of a times b is log of a plus b, right? So you'll use that identity in order to prove this. And you know, give them a shot, see if you can do them. You can prove all these things. I will do it on Tuesday, but this is really good exercise to see if you can just, symbol push around, okay? So prove the derivative of the exponential function is itself, and then prove these three identities. Okay? So any questions? Everyone feels okay? Yeah, okay, I think we can call it early. Yeah, let you digest this, because we did a lot, right? We did a lot.